I'm Jad Al, OPA project coordinator, and I will be delivering a presentation about our new software courses. As a start, OPA would like to thank the attendees of its online internship and the people who attended Prosper and WAFAM course last month. Our instructors gave a very positive feedback to each one of you, and they appreciated your active participation, dedication, willingness to learn new skills, and curiosity to ask deep and advanced questions to develop your knowledge in the software and the oil and gas industry in general. We hope to see you all in our upcoming courses, and you are now officially OPA ambassadors in the world. So about our two new software courses, OPA is delivering two new software courses that are Saphir Well Test Analysis and Gas Surface Network Modeling Training course, which will start on August 24 and August 30, respectively. These courses are conducted by excellent engineers with many years of work experience. The duration of each course will be 6 days. The duration per session will be 3 hours. There will be a 1-day break. Each day will have its own assignment. The cost for one course is $125. Taking the two softwares will save you $25 and will make you pay only $225 instead of $250. Saphir course will be in the period between 24 and 29 August. In this 6-day course, you will learn a lot. You will be familiar with the different types of pressure testing, flow regimes, diffusivity equation, and all the analysis techniques and Kappa Saphir features and data processing tools. You will learn how to perform QA/QC for the pressure data. And also, you will know more about the Wellbore models, reservoir models, well testing for fractured reservoir, and well testing design considerations. Regarding the gap training course, it's going to start in the 31 of August till 5 September. In this 6-day course, you will understand and learn how to build a gap model for water injection network, for production network, for gas injection network, match the pipeline correlations, perform network solving, connect the production network to gas injection network, add constraints to the system, perform network optimization, connect AMBAL model to network, and also perform prediction on gap model. OPA is providing a great offer for groups. That is, for a group of 2 participants, each person pay only $110 per course. For groups of 3 participants, each person pay $95 only per course. For a group of 4 participants, each person pay $80 only per course. And also for a group of 5 participants, each person pays $70 per course. This offer. OPA engages Lebanese students, graduates, and engineers who are interested in our upcoming software courses on Saphir and Gap. You can take one of these courses for only $50 instead of $125, or you can take both for. So how to apply? You can apply by filling the form that will Sam send now in the chat. So please all take a look in the chat and fill this link if you are interested in our 2 courses. Okay, thank you so much. And now, Omar, the stage is yours.
Thank you, Jad. Guys, you can find the link in the chat. My colleague Isam sent it, so you can register through this link. And you can contact us through our social media to know more about the courses and to have further discussions. And just a few simple rules before we start this session. Please write your full name so that we can take it into consideration when we take the attendance. And questions are allowed after the session ends in the Q&A session. And after the meeting, a feedback form will be sent to you, so please make sure to fill it in. And now I would like to introduce to you Engineer Hisham. Engineer Hisham is a senior reservoir engineer with about 10 years experience in the subsurface evaluation, reservoir characterization, and simulation at the reservoir at the Petroleum Company, GPC, in Egypt, many countries such as Saudi Arabia, Iraq, and Yemen, and he holds a bachelor's and master's degrees in petroleum engineering from Cairo University in Egypt. So now, Engineer Hisham, the stage is yours. Guys, just so that there is no confusion, I didn't ask you to write your names in the chat. Just make sure that you're logged in with your full name, but you don't need to write your full name in the chat. Engineer Hisham, can you hear us? Okay, you can start.
Okay, thank you so much, Omar. Thank you so much for all of you. Hello, everybody, and welcome to this webinar for well testing analysis principle and practice. I'm Hisham Mukhtar, senior reservoir engineer. So basically, as the name implies, this webinar is designed to introduce an overview of well testing principles and objectives, well testing types of well testing, and then the concept of flow regimes and pressure transient, different well testing surface equipment required while testing your well, and then we will discuss the concept of type curves and pressure derivative, and then we will explore different interpretation, and finally test the design and well testing design consideration. So your attention please, let's go directly to our agenda today. At first, introduction to reservoir engineering and basic principles, different types of pressure testing, basic theory of pressure transient, and the definition of the diffusivity equation, different analysis or differences between the traditional techniques of pressure transient analysis against the modern techniques like pressure derivative and the numerical modeling, different then well testing interpretation process, starting with Wellbore models, models, reservoir, and finally boundary models. After that, well testing interpretation process and the reservoir modeling, what's important to know in this stage, and finally pressure transient analysis golden rule you have to follow while working in pressure transient analysis and while modeling your pressure data. So, and now what is the reservoir engineering? At first, reservoir engineering is basically a branch of the petroleum engineering, which is concerned with handling the problem of the fluid flow in a porous medium. As you can see, if we consider a unit volume of our reservoir, so we have a matrix block and pore spaces in between. Within the pore spaces, we probably have reservoir fluids starting like water, oil, and gas, and so on. The basic principles for any reservoir engineering application is the first one is the Darcy's law of flow, or the flow rate equation, as we consider with a fluid flow in approximately. So the first principle for almost all reservoir engineering applications is Darcy's law, and as we have a specific, as we produce from specific subsurface volume or stored, so in this case we have to apply the second principle, which is material balance or continuity equation, such that the remaining volume will be the initial volume minus the produced volume. And the last one regarding the equation of a state model or BVT properties, basically the reservoir fluid properties like reservoir density, reservoir viscosity, and so on are typically dependent of reservoir pressure. So while production the reservoir, the pressure declines from the average reservoir pressure to the downhole pressure and then to surface or wellhead pressure. So in this case, it's important to characterize the properties of reservoir fluids while production using the third principle, which is equation of a state model. For complete system analysis, as you can see, if we consider the fluid flow from the bottom of the reservoir to the bottom of well up the production tubing, and then the wellhead, and as you can see, surface connections, processing facility, separators, and finally transportation. We also consider two additional models: well inflow model or IBR model, and to characterize the movement of fluid from reservoir to the bottom of the well. And the second model will be the well outflow or VLB model, to characterize the our fluid properties while production while movement from the bottom of well to the wellhead. So again, what is the well testing or pressure transient analysis? Simply, it's a signal sent to the reservoir. This signal is created by controlled open and shut-in of our well. This will be typically using surface control. As you can see, during the test, we create a pressure disturbance using a specific sequence of open and shut-in of our well, and the response, which is the pressure transient, will be recorded. So the recorded pressure transient will give us information about the near wellbore region at first, and then the reservoir properties, as you can see, like reservoir permeability, transmissibility, and so on. And finally, the reservoir boundary in terms of the distance of the boundary, type of boundary, and reservoir volume or reservoir connected volume. So simply, we create a pressure signal. We create a signal by controlled shut-in or build up and drawdown. The signal early response will regarding the information about wellbore and the reservoir. A late response will give us information about our boundary, and for long periods of the test, we can reservoir communication with other wells in our field. So as you can see, we have pressure response, pressure recorded versus time, and we have recorded flow rates versus time. The new wellbore effect is probably relating to wellbore storage and skin, the evaluation of the presence of formation damage or evaluation of the treatment operations. And for the middle time region, we can give more information about the reservoir properties in terms of reservoir heterogeneity parameters, and finally the reservoir boundaries or the reservoir pressure, reservoir shape, and volume. Applications of pressure transient analysis in exploration involves the determination of reservoir volume by information from boundary response and hydrocarbon type or productivity. Application in reservoir development, which is very important to reservoir engineers, is the determination of reservoir pressure, reservoir properties like reservoir permeability, formation damage, and how to optimize the production processes by creating or knowing more information about the productivity of our wells. And last, in the reservoir management stage, applications of PTA will be also a determination of drainage area of our well, evaluation of the stimulation treatment efficiency, and evaluation of and the identification of the formation damage. So similarly, the pressure transient analysis is the input signal will be the rate of change, as you can see. This is the input signal we induce to our reservoir system, while the output response will be the measured pressure versus time, bottom of pressure versus time. This is while recording process. While interpretation process, we probably have a input data, input model, which is recorded data or the real data, And then we have a mathematical model, or in other words, will be the diffusivity equation, that or the flow rate equation. By matching of the field data with this model or the parameters of the diffusivity equation, we will get the model that characterize our reservoir, and we finally will get the model parameters in terms of near wellbore, near wellbore parameters, reservoir parameters, and boundary parameters. So as you can see, as you can see, starting from the downhole, we have almost one main memory gauge to record pressure versus time, record pressure and temperature versus time. And then in the wellhead, we probably have a choke manifold and then the separators. On the wellhead, we have different measurements of the surface pressure, wellhead pressure, upstream and downstream pressure, fluids, separator or the surge tank, and almost we can get fluid samples for analysis. This is the period of testing and acquisition. While in the stage of interpretation, we almost have workstation or specific software like Saphir or alternatives like IHS. And this software will be used for loading our data and making the analysis or interpretation of our model. So the main required data for performing a pressure transient analysis is the flow rates, as you can see, and the recorded pressure, reservoir fluid properties, and other data like reservoir parameter like porosity, and well configuration like well radius, and so on. As you can see, we can get more important information about our reservoir boundaries, like the type of boundary, distance of the boundary, like this. Also, we can get more understanding of reservoir depositional environment, like in case of the complex depositional environment, like fluvial channels and sandbars, or even in case of injection. We can get more information about the flood front by changing of reservoir fluid properties, at least the changes of fluid viscosity of the and differences between the viscosity of the injected water and in contrast with the viscosity of the original reservoir fluid. So right now, the objectives of pressure transient analysis mainly is to evaluate the reservoir properties like reservoir permeability, skin, and fracture half-length, and so on, and get an estimate for the reservoir pressure that will be initial or alternatively the average reservoir pressure. The second objective, most important objective, is to get an estimation of the reservoir volume or reservoir shape and reservoir boundary distance. The main inputs for pressure transient analysis will be bottom hole recorded pressure, will be BWF, bottom hole flowing pressure, or BWS, bottom hole shut-in pressure in case of drawdown and build up respectively. And on surface, we have surface measurements of flow rates. Also, we need to have as input for pressure transient analysis fluid data like reservoir fluid parameters, formation volume factor, viscosity, and compressibility. And the last important input for pressure transient analysis is the well configuration and well geometry. The result is, on the other hand, will be the identification of production capacity of our well, the estimation of the average reservoir pressure, determination of reservoir limits, and reservoir specific or well specific parameters. So again, our interest is the bottom hole pressure, which is recorded with high frequency and high resolution. Almost we have one pressure recording every 3 or 5 seconds, and surface flow rates, separator surface flow rates recorded on 1 hour and half an hour basis. As you can see, this is a simple testing design. We have cleaning at first, cleaning after making a perforation of our interval, then build up interval, and two drawdowns. Most probably, the commonly used well testing program, as you can see, we have initial flow or after cleaning to evaluate the productivity of the well. Then initial shut-in to ensure the reservoir pressure is back to stabilize, or the initial reservoir pressure. As you can see, we have fluids in this curve, and in bottom we have recorded bottom well pressure. So in this period, the pressure is held constant as the initial reservoir pressure, while for the initial flow, as you can see, we have the first ever drawdown recorded in this well. Then the initial shut-in to ensure the stabilization of our pressure. Then we have a series of increasing fluid or increasing choke sizes, and finally extended, as you can see, extended flow period to ensure stabilize the flowing condition, and finally final build up to evaluate and make well testing interpretation. This is another example of real well testing because the data we have initial build up, as you can see, then different series of different drawdowns. The design of well test, as we will discuss at the end of the session, will be dependent of the reservoir fluid type and the required parameters you have to know about your well. Right now, it's important to understand what are the required well testing facility, well testing equipment while performing well testing, while performing pressure transient analysis for an oil well, for example. So as you can see, this is an overview of surface well testing equipment, starting from bottom to up, considering we have a completion string equipped with the memory gauges to record the pressure versus time, the pressure and temperature versus time. And in wellhead, we have Christmas tree, and then we almost have choke manifold, and then flow meters, and then we have 2 or 3 test separator, and then surge antenna, and finally to the flare or the burner room, as you can see. So the basic components, the basic surface, the most important surface equipment facility required while performing well testing are the Christmas tree, choke manifold, flow meter, test separator, and finally surge tank. Here again, focus on the downhole equipment. We have backer and memory gauge to record the pressure. As you can see, we have recorded pressure versus time against the production, the formation, the production or tested formation. And on surface, we have surface measurements after the test separator. We have recorded surface, also recorded pressure and the surface flow rates. The most important surface equipment, starting with choke manifold. The main function of choke manifold is to control the production rate while testing, and by using fixed or adjustable choke sizes. So the primary goal, the first control of the well was second important surface equipment is the test separator. We probably have at least 2-phase or 3-phase test separator. The main function of this is to make separation and metering for the produced fluid. We almost have separation of water as a separate phase, oil or condensate, and the main function of the surge tank is the flash of any dissolved in our liquid, and accordingly identify or determine the correction, the meter correction factor for the measured flow rate using operator. And the last test we almost have for production was we have the drawdown test. The drawdown test by definition means we producing our oil at a constant flow rate starting from time zero after shutting after a stabilization of pressure, and versus time. The second type of well test for production wells is the build-up test. Build-up test simply means starting the our well after production at constant flow rate and measuring the resultant pressure response, which will be BWS. On the other hand, for injection wells, we have injection test. Injection test like the drawdown, while we are injecting water, for example, injecting fluid at constant flow rate starting from time zero and measuring the pressure response versus time. And similar to build-up test, we have fall-off test, injection fall-off test, which are conducted by shutting well after injection at constant flow rate, and the pressure response is also recorded versus time. So again, to focus on the production well test, the first type is build-up, shutting after controlled production. As you can see, we have a build-up after a period of constant flow rate, a period of drawdown at constant flow rate, as you can see. The pros of this type of test is it's applicable to maintain the flow rate is constant at zero, which means our well is shut in. While the cons of this, we probably need to shut in our well for very long times, specifically for tight reservoirs. This will be required to reach stabilized reservoir conditions. While for drawdown, as you can see, we have a specific build-up, as you can see, stabilization in pressure, and then the drawdown at, by letting our well to be produced at constant flow rate. It's a very important test to identify reservoir limits and reservoir volume, but the cons of this, it's difficult. It's really difficult to keep the flow rate is constant, held at constant value, because any fluctuation in flow rate will typically distort the pressure transient. Therefore, in this case, as you can see, most well testing interpretation will be performed on build-up due to the R data is will have high accuracy, no noise in our data, so it's simply easily to keep your well producing at constant flow rate, which is zero flow rate. It's really applicable to make this, while for drawdown it's difficult to maintain your well producing at constant flow rate. So for gas wells, as you can see, we typically have two different types of tests. Primarily for gas wells, we have the two types of tests. As you can see, the first one is the isochronal test. The isochronal test basically involves the flowing our well at different flow rates of equal periods of equal duration, as you can see. While the last one will be extended flow rate to reach stabilization in the flowing conditions. And in between, as you can see, we have shut-in periods. The time of the period of the shut-in will be typically dependent of the reservoir parameter, and the length of the shut-in period will be designed to achieve to let the pressure transient to reach the static reservoir conditions. So simply for the coronal test, we have first drawdown followed by build up. The length of this build up period will be long to enable the pressure to reach the initial reservoir condition. Then we have second drawdown followed by build up and so on. The last one is the extended flow period. As you can see, we almost have stabilization in the bottom hole flowing pressure at this point. And finally, we have a final build-up for well testing interpretation. The second type of gas well test is the modified isochronal, which is typically similar to isochronal test. But the difference is the shut-in period. As you can see, these periods are of equal durations like the build-up periods, whether or not the pressure is reached stabilization. So the modified isochronal is most probably performed for gas wells. It's simply a series of drawdown followed by build-up of equal durations, whatever we reach the stabilization or not. And finally, the last build-up period, as you can see, is extended one to ensure stabilized flowing conditions. And finally, the final build-up. The main objectives of types of this test is to evaluate and identify the production capacity of our wells against different reservoir conditions. Second objective of this is to identify the absolute open flow of our well, and then to generate the IBR model and identify the productivity index of your well. Right now, I'm gonna talk about basic theory for pressure transient analysis and flow regimes. We have to know why performing on pressure transient analysis. So the flow regimes simply means the relationship pressure with time, while pressure transient analysis. The first ever flow regime for any production well will be the transient or unsteady state flow. In other words, IARF, infinite acting radial flow. In this regime, we almost have the relationship pressure with time, partial B over partial T will be function of R and T will function of distance, radial distance of the well and time. In this flow regime, the pressure transient simply doesn't reach the boundary of our reservoir. The second flow regime is the pseudo-steady state flow. In this regime, we have the relationship pressure with time, partial B over partial T will be constant, which means the pressure will changes at every point throughout our reservoir at the same rate. And this is very important to identify the reservoir shape, reservoir volume, and reservoir drainage area. The last flow regime is a steady state flow. In this regime, the relationship of pressure with time and changes of pressure with time will be zero, which means no change in pressure with time. Specifically in this type of flow regime, we probably have strong support of reservoir pressure like strong aquifer or active pressure maintenance operations like water injections and so on. So simply we have three different flow regimes. applied in well testing interpretation transient, where the partial B over partial T is a function of R and T. Pseudo-steady state or boundary dominated flow, partial B over partial T will be constant, and steady state, no changes in pressure with time. So again, and more specifically, the reservoir pressure distribution. As you can see, considering we have a shutting well in the center of a circular homogeneous reservoir. Therefore, in this case, the reservoir pressure will be uniform throughout the reservoir at the value of Pi, which is the initial reservoir pressure. We have to radius RW will be the wellbore radius, and RE will be the outer drainage radius of our reservoir. If we consider this well is allowed to produce at constant flow rate, as you can see, so in other words, we are creating pressure disturbance at the well at sand face. This pressure disturbance, as you can see, will move away in the reservoir based on the reservoir properties, and the rate of the movement and of the pressure transient will typically depend on reservoir parameters like K and phi, reservoir porosity, permeability, fluid viscosity, and total compressibility. This means at time T1, as you can see, the pressure transient will reach a radial distance as to R1, which is the drainage radius or the radius of investigation at this time. At time 5, as you can see, the pressure transient will reach the drainage or the radius of investigation as R5, and so on. As long as the pressure transient doesn't reach the reservoir outer boundary, so in this case we are talking about the transient or infinite acting radial flow, or in other words, the reservoir will acting as it is infinite in size, or mathematically this means that the RE or the outer radius of our reservoir will be infinity. So simply we have, as you can see, different relations of pressure with time. If the pressure doesn't change with time, we have steady state flow. If we have a constant rate of a change of pressure with time, we have pseudo steady state flow. If the pressure is changing with time as a function of R and T, so we are talking about transient or infinite acting radial flow. This is a very important concept for all well testing interpretation, well testing flow equation. It's important to understand this. We, as you can see in this configuration, we almost producing our wells at using this two scenarios. The first one is producing at constant flow rate, and the second one is producing at constant BW. However, in reality, the most applicable scenario is producing our well at constant flow rate. This is our assumptions in almost all pressure transient analysis applications. So the second flow regime, as you can see, is pseudo steady state or the boundary dominated flow. As you can see in mathematically, this will be presented by partial B over partial T constant, which means the pressure transient has reached the outer boundary of our reservoir. As you can see, we have here the pressure transient is moving to a radius R1 at time T1, radius R3 and time T3, and so on. While at this time where the pressure transient has reached the outer boundary of our reservoir RE. So we are in the beginning of the pseudo steady state flow period in the red colored curves, as you can see. At this point, the pressure transient starts to drop, or the average reservoir pressure starts to drop according to the boundary system. If we have no flow boundary, as you can see, we almost have the depletion in the average reservoir pressure from the initial value to lower values, as you can see, like the red colored curves. The almost parallel curves as the pressure will change at the same rate. So again, simply the infinite acting radial flow, the boundary has no effect on the pressure disturbance, while in the pseudo steady state or boundary dominated flow, the pressure transient or the pressure will decline or drop at a constant rate throughout the entire reservoir. So simply the main flow regime in well testing interpretation is the transient or the infinite acting radial flow. It's very important to identify reservoir parameters, reservoir permeability, and identify the average reservoir pressure, as you can see by interpretation of Horner plot in the traditional analysis of the well testing pressure build-up testing. In 1950s, the traditional well testing approaches are applied, like Horner plot MDH and MBH and so on. In 1970s, the introduction of the type curves in well testing interpretation. As you can see, type curves are log-log plots for dimensionless parameters. And most important, it's important to know in 1983, it's the introduction of the border derivative. Border derivative is typically the main concept or the main application for the modern well testing interpretation. We will focus on this part and this part at the end of this while talking about the reservoir modeling and well testing interpretation process. And in 1990s, the development of the first numerical models in well testing interpretation. So right now, it's important to know the definition of the diffusivity equation. Simply, the diffusivity equation is the mathematical model that will characterize our testing while modeling process. So the diffusivity equation is the main flow equation for well testing interpretation. Different assumptions are involved to develop this equation. The most important parameters are considering the reservoir is homogeneous reservoir, and Darcy's law is valid, and we almost have slightly compressible fluid and single phase flow. The main component of the diffusivity equation, like any other reservoir engineering applications, will be by default Darcy's law for radial flows, and second component will be the continuity equation or material balance equation, and the third component will be the equation of state or the fluid properties. Simply, we have the compressibility equation, as you can see, change in volume with pressure relative to the initial volume. So by combining the three components, combining the three equations together and rearranging, we will get the general form of the radial diffusivity equation, as you can see, this form. This term will be the diffusivity constant eta, as you can see. So the more generalized form of the diffusivity equation will be something like this, considering the diffusivity constant eta, which is a function of reservoir permeability and fluid viscosity, total compressibility, and reservoir and rock porosity. So here is the general form of the diffusivity equation is this form. If we're considering a steady state flow condition, that means partial V over partial T equals 0. So this term will equal 0. So in this case, this will be the form of the diffusivity equation for steady state flow conditions. Right now, and the methodology of pressure transient analysis is to get the solution of the diffusivity equation. Simply to solve the diffusivity equation, we have to consider two boundary condition and one initial condition. The initial condition is typically the initial reservoir pressure at time 0, and the boundary conditions considering we have a reservoir system, let's say we have wellbore side and boundary side. So the boundary conditions, the first condition is considering the well is producing at constant flow rate, and on the boundary side we are considering we have no flow boundary, which means we have transient or unsteady state flow condition. So this is the general form of the diffusivity equation. As you can see, by specifying initial and boundary condition, we have two common or two generalized solution for this equation: constant terminal rate solution, which based on the assumption of we are producing at constant flow rate, and the second one, constant terminal pressure solution. This is typically applicable for the water influx calculation. We are considering we have a support of our reservoir by external source like strong aquifer or even the water injection process or pressure maintenance operations and so on. More specifically, and the most important is to know the all well testing and pressure transient analysis techniques are dependent of the concept of constant terminal rate solution. In this solution, we have two different types of solution: is the EI function solution or exponential integral solution, and second one will be the BD or dimensionless pressure solution. So for the dimensionless, which is the commonly used in pressure transient analysis applications, if we consider this form of the Dawes law and to involve a specific boundary to be dimensionless, it's very simple to make it by, as you can see, we have units of psi. In this left-hand side, the assigned, and then we have also units of BSI. So the resultant term will be the dimensionless pressure, as you can see. And in the right-hand side, we have also dimensionless parameter, which is the dimensionless external drainage radius of our reservoir. Also dimensionless inch over inch, as you can see. So it's very simple to introduce the dimensionless parameters, as you can see, by rearranging our flow equations to get the units of psi times psi minus 1 and so on. Again, for the pseudo-steady state flow, we are considering partial B over partial T is constant, which means the reservoir pressure will decline. As you can see, reservoir, the pressure transient has reached the outer boundary of our reservoir, and then the reservoir, the average reservoir pressure will decline throughout the entire drainage area, the entire reservoir at the same rate. So at time t1 we have this value of the average reservoir pressure, and time t2 we have a constant value like this. So as you can see, the flow patterns are typically parallel, which means the pressure is changing at the same rate. What's important right here is to know the pseudo-steady state flow occurs regardless of the shape of our reservoir. So in this case, it's important to introduce a new parameter to account for any deviation from the ideal assumption of the diffusivity equation, which is considers the reservoir is circular reservoir. This term will be shape factor CA, as you can see, which is typically introduced to account any deviation from the ideal circular form of reservoirs. And at the end, we will have this relationship of the volumetric average reservoir pressure, and we have the shape factor C, as you can see in this term. Right now, it's important to know the relationships of pressure versus time. As you can see, if we are considering the Cartesian coordinates, as you can see, the relationship of BW versus time will follow this shape. Simply for the pseudo-steady state flow, as partial B over partial T is constant, so typically you will have a straight line on the Cartesian coordinates for during pseudo-steady state flow, while for the transient flow period, you have to plot your data on the semi-log coordinates BWF versus log time, as in this case, the pressure partial B over partial T will be dependent of, or will be function of R and T. So you, in this case, you will get a straight line during transient or infinite acting radial flow period on the similar coordinates. Unlike the Cartesian coordinates, we have straight line during pseudo-steady state flow period or boundary dominated flow period. Right now, it's important to characterize the existing information damage and to evaluate the stimulation process using a commonly known parameter, which is skin factor or skin effect. As you can see, this is the pressure profile for normally for any reservoir without any damage. The pressure starts to decline, as you can see, from the initial or average reservoir pressure, and then to a specific bottom hole flowing pressure at this value. For example, if we have a damage in the near around wellbore, this region will be defined as the altered zone of radius RS of our skin, and the permeability of this zone will be Ks, while the permeability of the rest of our reservoir will be K. So we have in actual damage of our reservoir, so we will have additional pressure drop. As you can see, we'll have a reduced bottom hole flowing pressure, and the difference between this value of the normal reservoir pressure profile and the profile in case of damage will be delta Bs, which is the pressure drop due to skin. Skin is typically will be a result of the invasion of drilling fluids, invasion of cement slurry, or injection process, or even the changes of any localized region around wellbore. This will create a new or damaged zone or a bad features of the region around the wellbore. On the other hand, if we have enhancement on the properties of the region around the wellbore, as you can see, so in this case, the bottom hole flowing pressure will be at this value, which is higher than the normal reservoir profile. This most probably will occur for stimulation process or hydraulic fracturing and so on. So simply back to the diffusivity equation and the solution of EI function solution. The assumption is we have uniform reservoir permeability across the entire drainage area of our reservoir. So it's important to introduce the pressure drop due to skin in the flow equation. Delta Bs will be, as you can see, the change of the normal reservoir pressure profile and the pressure profile in case of damage. So we have very important parameter, which is the SS or skin effect, which is a parameter of delta Bs. And as you can see, skin factor S is dimensionless, and it's a parameter to evaluate the value of damage or even to evaluate the stimulation process in case of stemmatic subsidizing or even hydraulic fracturing treatments. So again, another important parameter, which is the effective or apparent wellbore radius. By definition, as you can see, it's the actual wellbore radius times exponential of the skin effect. Simply, this term is introduced in flow equations for well testing to account for the presence of skin by changing the wellbore radius. Simply, if we have a existing skin damage, this will be simulated by considering we have a smaller wellbore radius, and alternatively, if we have enhancement or stimulation process or enhancement of the near wellbore region, so in other words, we have in increase in the wellbore radius, as you can see. So right now, the last two important parameters to evaluate the skin or the stimulation treatment is the typically the productivity index, which is the ratio of stabilized rate over the drawdown required to achieve this rate. As you can see, it's typically as a function of the skin. And the second important term, which is the flow efficiency, it's used to evaluate the skin damage or to evaluate stimulation treatment. As you can see, it's a relationship, a ratio of actual productivity index over the ideal productivity index. As you can see, it's typically the drawdown minus the pressure drop due to skin. So if we have a positive skin, or if we have existing from damage around the wellbore, so flow efficiency will be less than 1, and alternatively for stimulated well, we will have flow efficiency higher than 1, which means enhancement in the reservoir properties around the wellbore. Right now, the most important parameter in well testing interpretation is wellbore storage. Wellbore storage, basically in all well testing interpretation, considers the pressure disturbance due to the change, the instantaneous change in rate from, for example, from 0 to a constant value for drawdown, and change of instantaneous change and flow rate from specific value or constant value to 0 for buildup. While in reality, this is not applicable, as we have a wellbore, a fluid stored in the wellbore. So let's say the bottom hole pressure drops, so the wellbore fluids will expand, and then the initial fluid, while drawdown period, for example, the initial fluid at surface will be from the fluid stored in the wellbore, not directly from the sand phase. So as you can see, let's consider this relationship of fluid versus time. The diffusivity equation considers we have instantaneous change in fluid from 0 to a constant value, while in reality we have this shape. We have smooth or not instantaneous. We have regular increase in the sand phase fluid to finally approaches the surface fluid, and this period of time will be dependent of the parameter of Wellbore storage. So Wellbore storage is the period of time when the pressure transient will need to approach the sand phase or the reservoir fluid. This in case of drawdown, while in case in build up we have the opposite situation. As you can see, the assumptions consider its instantaneous change in fluid from constant value to 0, while in reality we have this trend, so the rate is changing, regularly changing from constant value to 0 due to the fluid expansion, the expansion of the fluid stored in the wellbore. This in case of buildup. So as you can see, and at this point, EI function solution becomes valid as the fluid recorded in this at this point is directly from our sand phase. Is the fluid recorded right here is directly from the reservoir. So we have to consider, or we have to introduce the definition of wellbore storage to account for this phenomenon. By definition, we have two different types of wellbore storage due to fluid expansion, by declining of the bottom hole pressure, and storage due to changing fluid level in casing during annulus. So by definition, wellbore storage coefficient will be a function of the change in wellbore volume with pressure in units of barrel PSI. So this is the general mass balance form. Sand phase fluid will equal surface fluid plus this term, which is a function of wellbore storage. As you can see, we have two different definitions for wellbore storage according to the type of storage. Right now, the main principle for all pressure transient analysis is the superposition. Superposition simply means the accounting for different wells existing in our fields, or accounting for the variable fluid. Simply pressure transient analysis considers we have, let's go to the diffusivity equation and pressure transient analysis techniques. Consider we have a pressure disturbance due to production at constant fluid from a single well, but actually we almost have more than well producing at the same time in the field. We have different wells producing at the same time. So in this case, principle of superposition is introduced to account for multiple pressure transient due to multiple wells instead of the single well, and account for the variable fluid instead of constant fluid, and account for the boundary effect itself by considering or by introducing the concept of virtual or image well. We'll discuss later in this session. So the first type of superposition is the superposition in space, which is typically to account for the pressure disturbance or pressure drop due to the production of other wells producing at the same time with the testing well or the active well. So as you can see, by applying the principle of superposition, the total pressure drop at well 1, for example, in case of drawdown, pressure drop, pressure difference will be Bi minus Bwf, will be pressure drop due to well 1 itself plus pressure drop due to well 2 and well 3 and so on. So this will be the form of EI function by applying principle of superposition. Also, to account the effective boundary, we typically apply principle of superposition by introducing an image well. As you can see, we have the active well or testing well that that has a specific distance L or R from no flow boundary, as you can see, like ceiling vault. This effect is typically simulated by considering we have an image well or virtual well located at equal distance from the boundary and producing as a constant a similar rate like the active one. So in this situation, the total pressure drop by applying principle of superposition will be pressure drop due to actual well plus drop due to the image well. Second type of superposition is superposition in time to account for, as you can see, the changes in flow rate instead of single flow rate, which is the assumption of the diffusivity equation or EI function solution or the constant terminal rate. In this situation, the total pressure drop will be pressure drop due to a change of flow rate Q1 minus 0 and changes between Q2 minus Q1 and so on. The principle is every flow rate change will create independent pressure response. Will create a pressure response which is independent from other pressure responses created by other rate changes. So simply, this is will be the principle of superposition in time to account for the changes of flow rate instead of considering constant flow rate. Right now, we will discuss the principle of type curves in pressure transient analysis and their applications. Simply, type curves are introduced in 1970. They are a graphical representation of the flow equations. They are typically plotted using dimensionless parameters. Simply to, as I said, simply to introduce the dimensionless parameter, it's simply to, for example, if we consider dimensionless pressure like this dimensionless parameter will be the pressure itself in units of psi times this group A or the variable A that will have the units of psi minus 1. So the resultant units of this variable will be dimensionless. So again, if we have the Diopsis law, as you can see, by rearranging, we can get something like this relationship. The dimensionless pressure will be this term times pressure difference in units of psi. So this term is typically will typically have the units of psi minus 1. So the final units of this parameter will be dimensionless. This group, as discussed, will be group A. Group A is typically a function of KH and mu and fluid. The most important function, most important parameter for this this variable of group A, K and mu and H, reservoir permeability and fluid viscosity, and the net P. So simply, if we introduce the logarithm of both sides, so we'll have this relationship. This will be the vertical, the vertical shift between log BD and the log of delta B. which is the vertical shift. Similarly, for dimensionless time, we can get the dimensionless time by, as you can see, by introducing the time times the group B. Group B will typically have the units of inverse of hour, and time will have the units of hours. So dimensionless time will be unitless, as you can see, and this will be group B. By plotting dimensionless pressure, as you can see here, versus dimensionless time over, and if we make if we plot this over the pressure difference versus time. So as you can see, we typically have vertical and horizontal shift between the two curves. If we the two curves are matched together and overlaid together, so the reservoir parameter will be at the end will be the parameter of our reservoir. So this is simply the concept of type curve matching or type curve approach, which is the main principles for modern pressure transient analysis. So as you can see, this is the shape of dimensionless type curves for Green Garden. As you can see, we have dimensionless in y-axis, dimensionless pressure versus dimensionless ratio, which is TD over CD, dimensionless Wellbore storage. And as you can see, we have a set of dimensionless, we have a set of type curves. The type curves, every one will have a specific value for this parameter, which is dimensionless characterization group. So the type curves are plotted on the dimensionless parameters, as you can see. Simply, we will overlay our field data to match one of these curves, and finally you will get the parameters of your reservoir. But is the problem right here is the similarity. As you can see, the similarity between the type curves. As you can see, we have different type curves. Most likely have the same shape, so it's difficult to correctly match your data using specific curve, as the curves are typically similar. So your data can be matched even using any one of them. So in this case, we typically have a large uncertainty to get the correct reservoir model, or to get the correct reservoir parameter. So this is the main problem for the Green Garden type curve. This issue will typically solve it by introducing the concept of the pressure derivative by Bolded in 1983. So the reason for this is to solve the problem of the similarity between the Green Garden type curves, as you can see, by introducing a new set of curves, which is a pressure derivative, which will improve the matching of our field data and eliminate the uniqueness of our problem, and confirm we are using the correct reservoir parameter. So again, Bourdon derivative, pressure derivative introduced in 1983. During Wellbore storage, as you can see, we have this relationship of pressure difference as a function of Wellbore storage, linear relationship. So the Bourdon derivative of pressure derivative will be T times partial delta V over partial T, as you can see. So if we give the derivative of this relationship, the resultant will be the same the same definition will be the same input, which is delta B. Therefore, during the complete Wellbore storage effect, we typically have a unit slope straight line, which means the pressure derivative and pressure difference curves has a unit slope straight line. As you can see, during this period, the pressure difference, this sets of curve, and this sets of curves are the pressure derivative will typically have a unit slope straight line. According to this definition of the pressure derivative, even in dimensionless parameters, the pressure difference and derivative, dimensional pressure and dimensionless pressure derivative will have a constant or a unit slope straight line like this. So this is the pressure derivative during Wellbore storage effect or Wellbore storage period. Next, during infinite acting radial flow period, as you can see, we have this flow equation. If we consider the pressure derivative, again, this T partial delta B by partial time, we'll have this constant, as you can see. So the pressure derivative will be flat or will have constant value during infinite acting radial flow. This value or this stabilization level will typically dependent of reservoir parameter K, reservoir and the fluid parameters K and mu, and typically the production rate and the perforation interval. Therefore, it's important to know the pressure derivative during infinite acting radial flow will be constant at a specific stabilization level dependent of reservoir and fluid parameters. By definition, the pressure derivative is the slope of semi-log plot plotted on the log-log plot as like this. So we have here a semi-log plot of delta B versus time. The slope of this, which is simply means the border derivative, as you can see by applying this definition. So we have in this case the log-log plot for pressure difference and pressure derivative, and typically during the infinite acting flow period, the pressure derivative will be flat or constant during this flow regime. The pressure derivative is most important to characterize the reservoir parameter and identify different flow regimes and make different pressure diagnostics of your recorded pressure versus time. So again, the main gains for applying pressure derivative is to have a clear signature of your reservoir and eliminate the similarity of the type curves by introducing new sets of curves for the pressure derivative. We typically have, as you can see, 3 different periods of our reservoir while pressure transient. Yes.
I think we passed our time. We should have some minutes for the Q&A session. So if you can stop here, maybe.
Okay.
Okay, so I will ask you the questions. We have them.
Okay, Omar, let me finish this part. I almost need 5 minutes.
Okay.
And I apologize for being late. Okay. So we have early and the middle time region. The early time region is typically dependent of Wellbore parameters at the starting or the early time. We have a unit slope straight line for Wellbore storage flow period, then a specific transition, and finally for middle time a stabilization level for the derivative, as you can see, for infinite acting radial flow. So simply, the pressure transient interpretation process, the field data is plotted at first, and then we are matching our data using a specific model, using a specific parameters of the pressure difference and the pressure derivative curves, as you can see. We can make evaluation for our reservoir according to three different periods of early time. As you can see, middle time, which is typically for the reservoir parameter and the good estimate for reservoir permeability and transmissibility, and finally the late time for identification of reservoir boundary effects. Let me skip this. Right now, reservoir modeling process and pressure transient interpretation. Simply, the pressure transient interpretation process passes through three different periods. Early time periods, the identification of the inner boundary of our system, which means we may have Wellbore storage, skin, partial penetration or fracturing or hydraulic fraction and so on. And next period is middle time region, is the identification of reservoir parameters, reservoir heterogeneity parameters. We probably have a homogeneous, or in other words, heterogeneous reservoir in terms of specific or corresponding parameters. And finally, the late time region is the identification of the reservoir boundaries. We typically have no flow boundaries or constant pressure boundaries according to the pressure response as our boundary. We have closed system or pressure support. In a modeling process, it's important to get match on the log plot, as you can see, and the history plot. Good match of build-up not necessarily to make a good match on drawdown. As you can see, we have a perfect match in this model in the build-up period, while the match of the pressure history of the other drawdown or even the this build-up period is not good enough. So in this case, it's important to know the model most probably wrong, as the models are a mathematical simplification of the complex reservoir condition, complex depositional environment. Second reason for this, you probably use not accurate measurements of flow rate, specifically during drawdown, or you probably, it's the third reason for this, you probably have problem in the nonlinear equation to match your data. And it's important also to keep your model matched at least at the end point like this blue colored circle, yellow colored circle, as you can see. This is our end point of our pressure response. The first end point is the initial reservoir pressure, and this end point, which is BWF at the starting of build-up and so on. And finally, the last build-up for this shutting period. Also, your data may be matched using different models. As you can see, this data is matched using two intersecting fault or composite reservoir. So in this case, it's important to integrate the other disciplines in your matching results to get more applicable test results in terms of geology and physics and even geophysics to ensure you have applicable test results. So I will stop right here. I just go through the last most important part is this. Pressure transient analysis golden rules you have to know while performing any transient pressure testing. First one is what happens suddenly is typically not a reservoir effect. You may have a problem in your recorded pressure and your problem in your memory gauge while recording. The second rule is the longer the flow period, the more information we can get from the pressure or the pressure transient analysis test. Endpoints are the guide of your interpretation, like the initial reservoir pressure. The fourth one is, which is most important, what the recorder or the memory gauge sees is not always the reservoir sees. It's important to consider the differences between the location of your memory gauge and producing information. Wellbore transient, like wellbore storage, may mask the reservoir transient. Also, when possible, it's important to use pressure gradient pressure stations before and after your test. And the also important rule, the software or the computer is only a calculator to perform specific calculations to solve specific flow equations, but it's not the interpreter. You are the interpreter for the test. And finally, and the most important rule while performing pressure transient analysis is start your problem simple and add additional scenarios to get your model matched. So thank you so much for joining me in this session. And now it's time for your questions. I also apologize for being late for this time.
Okay, Engineer Hisham, the first question is why do we need temperature measurement tool in the well testing?
Again, Omar, the objective of the temperature?
Yes, why do we need the temperature measurement tool in the well testing?
Typically, the memory gauges are recording pressure and temperature with time. Typically, in pressure transient analysis, our interest is the pressure versus time. In other situations, or the most probably in normal operations, we don't use the pressure as temperature measurements. We can make it as a reference of our the temperature of reservoir fluid to compare it with other measurements like the temperature recording while, for example, making fluid samples. So it's very important. It's important measurements for other applications, not for pressure transient analysis interpretation itself.
Okay, thank you. The second question is what's the function of the three-phase test separator?
Again, the function of three-phase test separator is to separate and meter the produced fluid. So considering we have oil reservoir, well, we probably have a gas in solution, and we may have in water associated with this oil. So the function of the test separator is a mix separation by gravity for these three phases, and create a metering or determination of the flow rates for every single phase. Typically, for three-phase separator, we have metering for the gas phase separately, and then oil, and the last phase is water. The important equipment or important facility after the tests or three-phase test separator is the surge tank. Surge tank simply used to flash off any remaining gas in this oil and used to identify the correction factor for the flow rate measurements recorded or calculated by the test separator.
Okay. Generally, what's the difference between build up and drawdown, and which one is more accurate?
Okay, the build up simply means we are shutting in our well after a period of production at constant flow rate. The opposite for drawdown, we are producing our well at constant flow rate after a period of shut-in or even at the initial reservoir conditions, starting from the initial reservoir pressure. For well testing interpretation, build-up is typically used due to it's more applicable to keep your flow rate constant by keeping it zero while shut in. While on the other hand, while drawdown, it's really difficult to keep your flow rate constant during drawdown, even at stabilized reservoir conditions. So the commonly used flowing period is the drawdown. Is the build-up, and drawdown may be used as a reference or to confirm the results of build-up if we have data without great noise. So in this case, we can also use the data from drawdown.
Okay, another question. What's the main difference between isochronal test and the modified isochronal test?
The main difference between the two tests is the duration or the time of the shut-in period between the production or drawdown periods. In the isochronal test, we typically have a sequence of drawdown followed by build-up. The length of this build-up period in the isochronal test will be the long to reach stabilized reservoir conditions, while for the modified isochronal test, the length or the period of drawdown and build-up will be equal. Whatever we are reaching stabilization, we achieve the stabilization or not. So the modified isochronal is the test interval for drawdown and build-up are equal, are the same period, whether or not we achieved stabilization during the build-up period.
Okay, one last question. Why do we use pseudo pressure for the gas wells in particular?
Pseudo pressure typically used for gas, as the gas properties are typically dependent of pressure. As we discussed in the assumptions of the diffusivity equation, we are considering we have slightly compressible fluid like black or even maybe volatile oils. While for gas, on the other hand, the gas properties like gas density, gas viscosity are highly dependent of pressure. So the relationship in this case, we must include the pseudo pressure, not pressure, as the relationship will be squared, not linear relationship of pressure versus gas properties, as typically they are dependent or highly dependent of pressure, unlike the oil. For example, slightly compressible fluids. We can consider the slight change in the reservoir and the fluid properties for oil, for example, with pressure. So it's important to use pseudo pressure, not the actual pressure or real pressure.
Okay, thank you a lot, Engineer Hisham, for this amazing session and for answering these questions. And I would like to thank all the people who attended this session and my colleagues who have made continuous efforts in all the sessions. And you can see this session on our YouTube channel, and the certificates will be sent within 1 week. My friend Isam will send the feedback link in the chat, so make sure to fill it in, please. And don't forget to follow us on our social media, LinkedIn, Instagram, Facebook, and YouTube to stay always updated about our news and our sessions and courses. And thank you a lot for attending today.
We have another question, Omar. Right?
We have some more, but I think our time is limited. We can take one more if you want.
Any questions, Omar, please?
Yes, I will give you one more question. What's the assumption when analyzing a shut-in period?
What is the assumptions when analyzing shut-in periods?
Mm-hmm.
Yes, the same assumptions will be valid for shut-in or build-up or even drawdown, but the difference is the pressure difference in drawdown, the pressure difference we are talking about PI initial pressure minus BWF bottom of flowing pressure, while for shut-in or build-up, the pressure difference will be the BWS bottom wall shut-in pressure minus the last recorded pressure during drawdown, which is BWF at delta T equals 0, which is the starting of build-up. So the assumptions are the same. The build-up, as I said, is more readily applicable for interpretation due to we are producing, the well is producing at constant flow rate or zero flow rate, while in drawdown we probably have highly noise. The noise of the data is most probably high regarding relative to the build-up periods or shut-in periods.
Okay, Engineer Hisham, thank you. My colleague Assam sent in the chat all our social media and YouTube channel and our WhatsApp, so you can check them in the chat. And also, we will see you tomorrow on our gap surface network modeling session at the same time at 7 p.m. Lebanon time, 6 p.m. Egypt time. So thank you a lot for attending today. Thank you, Engineer Hisham.
Thank you so much. Thank you for all of you, and hoping to see you in the upcoming events. I again apologize for being late in this session. Thank you so much.